Imagine a journey beginning quietly. At each moment, there are two different questions we might ask. The first question is local. Where are you now, and how fast are you moving now? This question concerns what is happening at one particular instant. It asks the immediate tendency of your position to change. The second question is global. How far have you traveled during the whole journey? This question concerns the combined effect of everything that happened between the beginning and the end. These are not the same question. A speed at one moment is not a total distance. A total distance is not the speed at one moment. Nevertheless, the two questions are deeply connected. The derivative is designed to answer the first kind of question. It measures local change. It takes a quantity that varies over time and extracts its instantaneous rate of change. The integral is designed to answer the second kind of question. It measures accumulated change. It takes a rate that varies over time and combines its contributions across an interval. The central fact of elementary calculus is that these two operations undo one another under suitable conditions. Differentiation takes a changing total and reveals the rate at which it is accumulating. Integration takes a rate and rebuilds the accumulated total. To understand why this is true, we will return repeatedly to one simple image. A journey is made from many tiny moments. Each moment contributes a tiny piece of change. The integral adds those pieces together. The derivative examines what happens when one more tiny piece is added. Let us begin with accumulation. Imagine a water tank being filled through a pipe. The flow rate is not constant. At some moments, water enters slowly. At other moments, it enters more quickly. Perhaps the pressure changes gradually, or perhaps someone adjusts a valve. At any given moment, the flow rate tells us how quickly the amount of water is increasing at that time. It might be described as a certain volume of water arriving during each unit of time. But a flow rate is not itself an amount of water. To find the total amount that has entered the tank, we must combine the water arriving during every part of the filling process. Consider a short duration of time. If the flow rate changes very little during that short duration, then the amount of water entering is approximately the flow rate multiplied by the duration. The idea is familiar even without formal calculus. If water enters at a constant rate for 10 seconds, the amount added is the rate multiplied by 10 seconds. When the rate is changing, we cannot use one rate for the entire process. Instead, we divide the time into shorter pieces. During the first short piece, we use the flow rate appropriate to that piece. During the next short piece, we use the new flow rate. Each short time interval contributes a small amount of water. We then add all these small amounts. If the time pieces are fairly large, this procedure gives only an approximation. The flow rate may change noticeably inside one piece. The chosen rate may represent the beginning of the piece, the end of the piece, or some intermediate moment, and different choices may give different answers. The integral emerges when we make the time pieces smaller and smaller. As the pieces become shorter, the flow rate has less opportunity to vary within each one. The approximation becomes more faithful to the actual filling process. Under appropriate assumptions, these increasingly refined approximations approach a single limiting value. That limiting value is the integral of the flow rate over the chosen time interval. The same idea appears in walking. Suppose a person walks along a straight path. Their speed changes continuously. They begin slowly, increase their pace, slow down near a crossing, and then continue. During a very short interval of time, the speed is almost constant. The distance traveled during that interval is approximately the current speed multiplied by the short duration. Each smaller interval contributes a small piece of distance. The total distance is obtained by adding all those pieces. Again, if the intervals are not very short, the approximation may be crude. But as the intervals become smaller, the estimated contributions represent the actual movement more accurately. The integral is the limit of this process of increasingly fine addition. It is worth repeating the central intuition. An integral does not merely mean adding values of a rate. A rate has units involving time, such as distance per unit time or water volume per unit time. To obtain an actual contribution, the rate must be combined with the duration. The integral adds quantities that are approximately rate multiplied by tiny duration. The duration becomes tiny, but the contribution does not disappear from the reasoning. There are more and more tiny intervals, and their combined effect approaches a finite total. We should also be careful with the word tiny. In rigorous calculus, we do not assume that there are literal time intervals of a smallest positive size. Instead, we construct finite partitions of the time interval and study what happens as the largest piece in the partition approaches zero. The integral is defined through a limit. The language of tiny intervals is therefore intuitive language. It describes the limiting mechanism without claiming that time is physically made of indivisible pieces. Let us pause and reflect. A changing rate produces many local contributions. Each contribution is approximately the rate during a short interval multiplied by the length of that interval. The integral is the limiting total obtained when the intervals become arbitrarily short. Now we introduce the idea that makes the connection with derivatives especially clear. Fix the beginning of a journey. For example, let the journey begin at 9 in the morning. Instead of fixing the ending time, allow the ending time to move forward. At 9:15, we can ask for the total distance traveled from 9 until 9:15. At 9:30, we ask for the total distance from 9 until 9:30. At 10, we ask for the total distance from 9 until 10. Every possible ending time produces a corresponding accumulated distance. This means that accumulated distance is itself a function of time. The input is the chosen ending time. The output is the total distance accumulated from the fixed beginning until that ending time. This point is fundamental. An integral need not produce only one number. When one endpoint remains fixed and the other endpoint is allowed to vary, integration produces a new function. Imagine a bathtub being filled. At each moment, the bathtub contains a different total amount of newly added water. The total accumulated water begins at zero at the chosen starting time. It then grows as water continues to enter. If the inflow becomes faster, the accumulated amount grows more steeply. If the inflow becomes slower, the accumulated amount still grows, but less rapidly. If the inflow stops, the accumulated amount becomes constant. The accumulated amount records the entire history of the flow from the starting time until the present moment. Yet it also has a local rate of change at the present moment. This brings us to the crucial question. If we differentiate this accumulated total function, what do we obtain? Take a particular ending time. The accumulated total includes everything that entered from the initial time up to that ending time. Now move the ending time forward by a small duration. The new accumulated total includes everything counted before, plus whatever enters during the final small interval. The difference between the new total and the old total comes only from that final interval. All earlier contributions appear in both totals and therefore cancel when we subtract. Suppose the current flow rate is known. During a sufficiently short final interval, continuity tells us that the flow rate remains close to its value at the endpoint. The newly added water is therefore approximately the current flow rate multiplied by the length of the small interval. To calculate the derivative of the accumulated total, we divide the change in total by the change in time. The approximate change in total is the current flow rate multiplied by the time increment. Dividing by the time increment leaves approximately the current flow rate. As the time increment approaches zero, the approximation becomes exact, provided the flow rate is continuous at the moment under consideration. Therefore, the rate of change of the accumulated amount equals the original flow rate. Let us state this slowly. The rate of accumulation equals the quantity being accumulated. When we accumulate velocity over time, the rate at which displacement accumulates is velocity. When we accumulate water flow over time, the rate at which water volume accumulates is the flow rate. When we accumulate electrical current over time, the rate at which electric charge accumulates is the current. When we accumulate a population growth rate over time, the rate at which the accumulated population change grows is the growth rate. This statement is one half of the Fundamental Theorem of Calculus. In precise terms, suppose a function describing a rate is continuous over an interval. Construct a new function by integrating that rate from a fixed starting point to a variable endpoint. Then the new function is differentiable, and its derivative at each point is the original rate at that point. The continuity assumption ensures that, on a sufficiently short interval near the endpoint, the rate is close to its endpoint value. More advanced versions of the theorem weaken this assumption, but continuity gives the cleanest setting for understanding the idea. Another way to say this is that integration creates an accumulation function, and differentiation opens that function at its moving edge. The derivative detects the contribution entering through the final boundary. The entire past is stored in the accumulated total, but when the endpoint moves slightly, the past does not change. Only the new final piece matters. That is why local operation can recover the original local rate from a global accumulation. Let us now turn the relationship around. Suppose we already know a function whose derivative is a given rate. Such a function is called an antiderivative of the rate. An antiderivative is a quantity whose instantaneous rate of change matches the known function. For example, if a known function describes velocity, then an antiderivative can describe position. If a known function describes the rate at which water is entering the tank, then an antiderivative can describe the amount of water apart from the choice of an initial amount. The phrase apart from the choice of an initial amount is important. A rate of change does not determine an absolute starting height. Two functions can have exactly the same derivative while differing by a constant amount. Imagine two identical roads climbing through the same sequence of slopes, but one road has been lifted vertically above the other. At every corresponding point, the steepness is the same. Their heights differ, but their rates of change do not. Similarly, two position functions may describe objects moving with exactly the same velocity while beginning at different locations. One object may remain 10 meters ahead of the other throughout the motion. Their positions differ by a constant, but their velocities are identical. Differentiation removes constant vertical shifts because a constant does not change. This is why a given rate is not just one antiderivative, but an entire family of antiderivatives differing by constants. Integration over a fixed interval avoids this ambiguity by using endpoint differences. Suppose we choose any antiderivative of a continuous rate. The total accumulation between a starting time and an ending time is obtained by taking the antiderivative value at the ending time and subtracting its value at the starting time. This is the second main form of the fundamental theorem of calculus. Why does subtraction remove the ambiguity? If we replace the antiderivative by another one shifted upward by a constant, then both endpoint values increase by that same constant. When the starting value is subtracted from the ending value, the added constant cancels. Therefore, every antiderivative gives the same endpoint difference. Consider altitude along a hiking route. Suppose a function records altitude as the hiker moves along the path. The rate of change of altitude with respect to distance along the path describes the local slope. If we accumulate the sine slope contribution from the beginning of the route to the end, we obtain the net change in altitude. This net rise equals the ending altitude minus the starting altitude. The hiker may climb, descend, and climb again. The endpoint difference does not record the total amount of upward motion. It records the net change. Descents count negatively because the slope is signed. This endpoint principle is extremely general. If a changing quantity has a known rate, then the total signed change in the quantity over an interval equals its final value minus its initial value. To see why, imagine dividing the interval into many small pieces. On each piece, the change in the quantity is approximately its rate multiplied by the duration. Adding these local changes produces a chain of successive differences. The increase from the first moment to the second is added to the increase from the second moment to the third, and so on. Intermediate values cancel. What remains is the final value minus the initial value. In a rigorous proof, one uses the mean value theorem or the first part of the fundamental theorem, depending on the chosen development. The intuitive cancellation of intermediate changes is the finite version of the same structural fact. Let us pause and connect the two forms of the theorem. The first form begins with a rate. It constructs an accumulation function and says that differentiating this function returns the rate. The second form begins with an antiderivative. It says that integrating the derivative over an interval returns the net change in the original function. In one direction, accumulation followed by differentiation recovers the integrand. In the other direction, differentiation followed by integration recovers the original function up to its starting value. A derivative forgets constants, so an integral can restore only the change unless an initial condition is provided. We can now place all of these ideas inside one continuous motion story. Imagine a slow train traveling along a straight railway line. At every moment, the train has a position. We choose a reference point along the railway and describe the train's position relative to it. Position is signed. A location on one side of the reference point may be treated as positive, while a location on the other side is treated as negative. The choice of orientation is arbitrary, but once chosen, it must be used consistently. The derivative of the train's position is its signed velocity. Signed velocity contains both speed and direction. A positive velocity means the train is moving in the chosen positive direction. A negative velocity means it is moving in the opposite direction. A velocity of 0 means the position is momentarily not changing. Suppose the train moves forward for a while, stops at a station, reverses slowly, and then moves forward again. If we integrate the sign velocity over the entire journey, we obtain the train's net displacement. Net displacement is the final position minus the initial position. Forward motion contributes positively. Backward motion contributes negatively. A backward segment can cancel part of an earlier forward segment. For example, imagine that the train travels 10 kilometers forward and then 3 kilometers backward. Its total distance traveled is 13 kilometers, but its net displacement is 7 kilometers forward. The integral of sign velocity gives 7 kilometers because the backward motion contributes negatively. The integral of speed gives 13 kilometers because speed is non-negative. Every piece of movement contributes positively regardless of direction. This distinction is important. Velocity is the derivative of sign position. Speed is the magnitude of velocity. Integrating velocity gives displacement, while integrating speed gives total distance traveled. The fundamental theorem applies directly to position and velocity. Since velocity is the derivative of position, the integral of velocity between two times equals the position at the later time minus the position at the earlier time. If we instead integrate speed, we obtain the total length of the path traced by the train. This total distance need not equal the difference between the endpoint positions, because reversing direction creates additional travel without necessarily creating additional net displacement. The motion example also clarifies what happens when velocity changes sign. The accumulated displacement function may increase during forward motion and decrease during backward motion. Its derivative remains the sign velocity at each moment. By contrast, accumulated total distance never decreases. Its derivative, wherever the speed is well behaved, is the non-negative speed. Let us pause and reflect once more. A derivative reads the local behavior of a function. It tells us how the output is changing near a particular input. An integral builds a global quantity from local contributions. It combines changes over an entire interval. The fundamental theorem says that these operations are not merely related by analogy. They are mathematically inverse in a precise sense. Yet the word inverse requires care. Differentiation loses constant information. If two functions differ only by constant, they have the same derivative. Therefore, indefinite integration produces a family of antiderivatives rather than one uniquely determined function. Definite integration, however, calculates a change between endpoints. Endpoint subtraction removes the arbitrary constant, so the result is unique. There is another subtle point worth making. The derivative is local, but it is defined by a limit involving nearby point. The integral is global over an interval, but it is also defined by a limit involving increasingly local pieces. Both operations rely on the same broad mathematical strategy. We approximate using finite quantities, refine the approximation, and identify a limiting object. For the derivative, we compare changes over shorter and shorter intervals surrounding a point. For the integral, we add contributions over finer and finer partitions of an interval. In the derivative, shrinking an interval reveals local rate. In the integral, shrinking all the intervals makes the global sum accurate. The two limiting processes fit together because the small change in an accumulation function is controlled by the contribution from one small final interval. The fundamental theorem therefore expresses a compatibility between two limits. One limit defines accumulation from local pieces. The other limit examines the local growth of the resulting accumulation. Continuity ensures that the local rate behaves regularly enough for these limits to agree in the elementary setting. It is worth repeating the two original questions. What is changing now? What changed altogether? The derivative answers the first question. It examines a function near one moment and reports its instantaneous rate of change. The integral answers the second question. It collects contributions across a whole interval and reports their accumulated effect. The fundamental theorem is the bridge between them. It tells us that the accumulated effect has the original rate as its derivative, and that accumulating a derivative gives the difference between endpoint values. This bridge explains why antiderivatives are so useful for evaluating definite integrals. Directly returning to finer and finer sums would often be difficult. The theorem allows us instead to find any function with the required derivative and then compare its values at the endpoints. The computational method rests on a structural theorem. We can replace an enormous limiting sum by two function evaluations because all intermediate changes are already encoded in the antiderivative. This is one reason calculus becomes a working language rather than a collection of separate techniques. Position, velocity, acceleration, flow, mass, probability, charge, energy, and many other quantities can be related through rates and accumulations. The same pattern extends beyond ordinary functions of one variable. In several variables, derivatives describe local linear change, while integrals combine local contributions over curves, surfaces, and regions. The fundamental theorem becomes a family of results. A line integral of a gradient depends only on endpoint values. A circulation around a boundary can be related to rotation across the enclosed region. Flux through a boundary can be related to divergence inside the region. The precise hypotheses and geometric objects change, but the recurring principle remains recognizable. Local change, accumulated over a domain, becomes a boundary difference. This principle also appears in probability. A density describes how probability is distributed locally, while a cumulative distribution function records the total probability accumulated up to a chosen point. Under suitable regularity, differentiating the cumulative function recovers the density. In differential equations, a derivative specifies how a system evolves locally. Integration reconstructs a trajectory from that local law, once an initial condition is supplied. In each setting, local information alone does not determine an absolute state. An initial value or boundary condition is needed. This is the same constant ambiguity that appears when finding antiderivatives. Let us now allow the discussion to widen slightly. The relationship between derivatives and integrals is one example of a broad mathematical habit, understanding a structure by separating it into elementary changes and then determining how those changes recombine. Abstract algebra follows a related habit, although its objects and operations are different. In algebra, we study sets equipped with operations and ask which features remain unchanged under structure-preserving transformations. Groups organize symmetry. Rings organize addition and multiplication. Fields provide settings in which arithmetic operations behave with strong regularity. Extensions enlarge a field so that previously unavailable elements become present. Polynomial roots that do not exist in the original field may appear in a suitable extension. The larger field records not merely new numbers, but new structural relationships. Modules generalize vector spaces by allowing scalars to come from a ring rather than necessarily from a field. They reveal how algebraic objects can be assembled, decomposed, and compared. Under favorable hypotheses, a complicated module can be expressed through simpler components. Polynomial factorization is another form of decomposition. A polynomial may be broken into factors whose roots and multiplicities expose its internal structure. Over a larger field, a polynomial may split more completely, just as a global calculus problem may become transparent after identifying the right local contributions. Symmetry enters through the ways roots can be permuted while preserving all algebraic relations among them. These permitted permutations form a group. The group captures what remains unchanged even as individual roots exchange their roles. Questions of solvability then become questions about structure. Whether polynomial roots can be expressed through repeated arithmetic operations and extraction of roots is controlled by the internal organization of the associated symmetry group. These algebraic ideas are not applications of the fundamental theorem of calculus. The theories are formally distinct. The connection lies in mathematical method. Calculus studies a changing whole by examining local behavior and accumulation. Abstract algebra studies a complicated system by identifying operations, invariants, decompositions, and symmetries. In both cases, understanding comes from discovering what information is preserved and what information is lost. A derivative preserves local change but loses constant height. An algebraic homomorphism preserves specified operations but may identify distinct elements. An integral reconstructs accumulated change once boundary or initial data is supplied. An extension supplies a larger setting in which hidden algebraic structure becomes visible. A decomposition replaces one complicated object by simpler pieces together with rules for recombination. A symmetry transformation changes presentation while preserving essential relation. Let us end by returning to the journey. At one moment, calculus zooms in. It asks how position is changing now. It replaces the whole journey by a local rate. Then calculus adds everything back together. It takes the rate from each part of the journey and accumulates the contributions from beginning to end. The derivative moves from the whole function to its local change. The integral moves from local contributions to a global total. The fundamental theorem says that these movements fit together. The rate of the accumulated total is the original rate. The accumulation of a derivative is the total change between endpoints. The derivative forgets where the journey began, but remembers how it moved. The integral rebuilds the change in position, provided we specify where to begin. Local change and global accumulation are therefore two descriptions of the same evolving process. This pattern belongs to a larger mathematical search for structure. Fields are enlarged through extensions. Modules are understood through decomposition. Polynomial roots are organized by symmetry. Solvability is determined by what those symmetries permit. Across these theories, mathematics advances by identifying which transformations change appearance and which relationships remain unchanged. Calculus zooms in to reveal change and then adds the changes to recover the whole. Abstract algebra changes the language or representation of an object and then asks what structure survives. In both cases, the enduring object of study is not merely a calculation. It is the pattern preserved through the calculation. And so the journey closes with a quiet unity. We begin with a whole, separated into meaningful local pieces, understand the rules governing those pieces, and assemble them again. What remains unchanged through this process is the structure mathematics seeks to reveal.